Welcome to an overview of Highway Safety Network Screening presented by PennDOT, the Pennsylvania Department of Transportation. The purpose of this video is to be a resource to transportation planners and engineers, enabling them to understand how PennDOT conducted network screening and what the results mean, and to encourage the use of network screening results for safety analysis and decision-making, and ultimately decreasing the frequency and severity of crashes in the Commonwealth. In this video, you will learn the purpose and definition of network screening, the components, terminology, and analytical steps of the network screening process, and how to understand and use the results of PennDOT's network screening to make safety improvement decisions. What is network screening? A method from the Highway Safety Manual, or HSM, network screening compares expected crash frequencies and crash severities to historical crash data based on Part C of the HSM. This comparison helps agencies evaluate many facilities as well as identify and prioritize locations that are likely to respond to safety improvement investments. The Federal Highway Administration says that employing traditional network screening with systemic safety analysis can be an agency's first step toward a comprehensive safety management program. Network screening is the first step in the roadway safety management process in Part B of the HSM. It is followed by these steps: diagnosis, select countermeasures, economic appraisal, prioritize projects, and safety effectiveness evaluation. The roadway safety management process parallels the method by which PennDOT selects and evaluates projects for Federal Highway Safety Improvement Program, or HSIP funds. What makes network screening different from other crash analysis methods? Instead of focusing on traditional crash rates and hotspots, network screening uses an HSM-based analysis that considers area types, roadway geometry, and traffic control characteristics. Network screening is data-driven and uses many factors, not simply traffic volume, to predict crashes. Because there is a nonlinear relationship between traffic volume and crash frequency, traditional crash rate methods paint an incomplete picture. These older crash rate methods also do not account for known risk factors associated with geometry and operations. For example, according to the HSM, rural two-lane segments with curves will have more crashes than rural two-lane road segments without curves. By incorporating this prediction into network screening, we can better account for the well-established relationship between horizontal curvature and crash frequency. This approach also helps us avoid over-prioritizing safety improvements for road segments with curves simply because they have curves. Network screening is also less reactive than other crash analysis methods because it considers three types of crash frequencies, each typically reported as crashes per year for a given study location. Network screening considers predicted crashes, the frequency or number of crashes predicted by a safety performance function, or SPF. Observed crashes, the frequency or number of police-reported crashes. And expected crashes, a weighted average between predicted and observed crashes. We'll cover expected crashes in more detail later in this video. To predict crashes, according to Part C of the HSM, safety performance functions, or SPFs, should be calibrated to local conditions in each state or replaced with state-specific SPFs. These approaches account for state-to-state differences in police crash reporting requirements and practices, terrain, weather, driver behavior, design practices, land use, and other factors. For conventional roadways, PennDOT developed our own SPFs. For freeways and ramps, we calibrated SPFs from the HSM. To learn more about SPFs, check out our PennDOT 1.5-day HSM training courses. So, how many SPFs are there? Here are the conventional roadway site types for which SPFs are available in Pennsylvania. Each cell on the table, or site type, is associated with multiple SPFs. At a minimum, there are SPFs for total crashes and SPFs for fatal plus injury crashes. Additionally, some site types have SPFs for each engineering district instead of statewide SPFs. Throughout this video, we refer to crashes for simplicity, but using SPFs further breaks down crashes into fatal and injury or property damage only crashes. The HSM also has SPFs for these freeway and ramp site types. Each site type has multiple SPFs for different crash types and severities. We'll explore these site types in more detail later in this video. Once SPFs, either from the HSM or PennDOT, predict crashes, the network screening process computes the expected number of crashes. For example, suppose the HSM predicts a site will have 4.2 crashes per year. However, observed data for the last 5 years indicates there have been an average of 7 crashes per year. So, how many crashes should we expect next year? 4.2? 7? Something in between? According to the HSM, the expected number of crashes will be something between 4.2 and 7. The HSM accounts for regression to the mean, or the idea that crash frequencies may vary year to year, but in the long term, they will return to the predicted average for a given site. So, for the site in question, we should expect crashes to trend down from the observed value of 7 per year toward 4 per year. The specific number of expected crashes is determined with a statistical technique called the empirical Bayes or EB method. The EB method computes expected crash frequency by assigning a weight to the predicted crash frequency and the observed crash frequency, and then comparing the two. The weight of the predicted crash frequency is based on a statistical measure called an overdispersion parameter, which describes how well the SPF fits the data used to create it. The weight of the observed crashes is based on their number. More crashes mean greater reliability of historical data. In this example, the EB method gives us an expected crash frequency of 5.8 for next year. A similar calculation could be performed if there were fewer observed crashes than predicted crashes. We would expect more crashes next year than were observed annually over the last 5 years. Finally, we compare the expected average crash cost to the predicted crash cost for each site, considering cost accounts for both the frequency and severity of crashes. If a site has an excess of expected crash costs, the site is generally a good candidate for safety improvements. If the cost of expected crashes is less than the cost of predicted crashes, the site is generally not a good candidate for safety improvements. The number and severity of crashes over what's expected also determines whether a site is a good candidate for improvements. For example, a site with 10 excess crashes is likely a better candidate for safety improvements than a site with 1 excess crash. Sites with high excess costs are most likely to respond to safety improvements because they are experiencing more crashes than they theoretically should based on their area type, facility type, AADT, and geometric characteristics. Before we take a look at the details of PennDOT's network screening, let's revisit these site types and provide some examples. SPFs are developed separately for urban and rural area site types. Urban areas are areas within urban boundaries where the population is greater than 5,000. Urban areas include suburban areas. Rural areas are outside urban boundaries where the population is less than 5,000. PennDOT's network screening uses U.S. Census Bureau data to determine if sites are located in urban or rural areas. Conventional roads in urban areas may be arterials or collectors. Conventional roads in rural areas may be two-lane, two-way highways, or multi-lane highways. For network screening, all of these roadway facilities are broken up into intersections and segments. An intersection is the crossing of two public roadways. Intersections can be signalized or stop-controlled. They can also have different numbers of approaches and other geometric and operational differences. For the purpose of network screening, crashes within 250 feet of an intersection are generally associated with that intersection instead of with the adjacent road segments. However, in some cases, another intersection is within 250 feet of the intersection of interest. When analyzing these locations, it is necessary to shorten this distance. For example, at this intersection in Philadelphia, including crashes 250 feet away would actually include crashes at other intersections. Here, we used a 50-foot crash buffer instead. Next, we have segments. For segments, PennDOT's roadway management system, or RMS segments, were used. These segments are generally similar enough from start to end that it is appropriate to analyze them as a single HSM segment. For multi-lane roads with secondary segments, the primary and secondary segments were combined to be a single HSM segment unless the roadway consisted of one-way streets. For freeways and ramps, there are 4 site types: freeway segments, speed change lanes, ramps, and ramp terminal intersections. Freeway segments are sections of mainline freeway between ramps. Speed change lanes are where ramps intersect freeways. Speed change lanes can be taper style or parallel style and can serve entrance or exit ramps. The limits of a speed change lane are between the gore point and the taper point. Ramps that add or drop lanes onto the freeway do not have speed change lanes. Ramps connect freeways to crossroads or other freeways. Types of ramps in the HSM include entrance ramps, exit ramps, connectors, which link 2 freeways, and collector-distributor roads. Ramp terminal intersections are where ramps intersect with crossroads. Ramp terminal intersections may be signal or stop controlled. The HSM provides SPFs for many different ramp terminal intersection configurations, which correspond to typical interchange forms. Those forms are shown here. Ramps without control at the crossroad do not have a ramp terminal intersection associated with them. Now that you know the basics about the HSM and network screening process, let's talk about what PennDOT's Highway Safety section has done and how you can use it. PennDOT conducted our first network screening in 2017. In 2021, we conducted a second network screening using updated data, new sites, and newly developed SPFs for collectors. This screening was the first to include freeways and ramps. The 2021 network screening accounted for crash severity for the first time. For greater consistency statewide, we also used a new source, census data, to determine urban and rural area types. A third network screening was conducted in 2024. This screening expanded the segment analysis to nearly all PennDOT-owned conventional road segments in the state. For freeways, entire interchanges were analyzed for the first time by grouping together ramps, ramp terminals, and speed change lanes. Also for the first time, a statewide screening of single-lane roundabouts was conducted. How were sites selected for network screening? Intersections and segments were selected using similar thresholds. For intersections, we analyzed all intersections that had been analyzed in the previous 2 screenings. Additionally, we added 100 intersections each in 13 higher population counties. To identify segments, we started with the full list of RMS segments. Limited access segments and ramps were removed since they were analyzed in other parts of the network screening effort. Primary and secondary segments were combined unless they were one-way streets, and some unusual state routes like rest areas and park and ride lots were removed. All remaining segments were analyzed. In total, we studied 9,000 intersections and 57,000 segments statewide. For freeways and ramps, we developed an inventory of every speed change lane, ramp, and ramp terminal intersections across the state using Google Earth and ArcGIS. The ramps, ramp terminal intersections, and speed change lanes were then grouped into interchanges. We used Roadway Management System, or RMS segments, as the basis of freeway segments. We conducted a preliminary analysis of the entire state using the portion of the SPF with AADT variables. This preliminary analysis identified top sites, which we then analyzed with the full HSM method. There is an intersection spreadsheet and a segment spreadsheet for each county. There is also a statewide freeway and ramp spreadsheet. The spreadsheets are sorted from highest to lowest excess cost. If this sounds like a lot to keep track of, don't worry, we've got maps. There are 2 online GIS maps for network screening, one for the sliding window analysis and one for everything else. Let's start with the one for everything else. When you first access the map, you'll see this legend that explains the color coding. Sites that are red, orange, or yellow have excess crash costs. These sites are generally good candidates for safety improvements. Moving to the map, everything is turned on to start with. Make sure your browser window is maximized to the full screen in order to have the map displayed properly. The buttons at the top can be used to reduce the amount of data shown. Clicking on Top 100 only shows 100 conventional road segments and intersections that had the highest excess crash costs statewide. Now let's turn everything on again and filter the results. The Filter button enables you to turn off green sites and only see sites with positive excess crash costs. The Layers button lets you turn off certain categories of sites. Let's turn off everything except for HSNS urban segments and HSNS rural segments. We still have green sites filtered out, so what remains is a map of conventional road segments with excess crash costs. If we zoom in and click on a segment, we can see data such as the county, SR, segment, and excess crash cost value. Now let's take a look at the second map that shows the results of the sliding window analysis. This map may take a little while to load. Once data fills out the entire state, you can zoom in and click on a line. Unless you are very close to the beginning or end of an SR, clicking on a line will actually be clicking on several overlapping sliding window segments. Use the arrows at the bottom of the pop-up to advance through each of the sliding window segments associated with the point at which you clicked. The pop-up box shows the excess crash costs for each of those segments. These are the network screening maps. Both of these maps can be accessed through PSIT or CDART. To take a closer look at the network screening results, you can access the underlying analysis in the spreadsheets. These spreadsheets are not priority lists. A site listed on this spreadsheet is not necessarily a candidate for safety improvements and may not have excess crashes. These site lists are meant to help PennDOT, MPOs, and municipal staff identify potential locations for safety improvements, which can be determined through additional study. Each spreadsheet has two worksheets, one for rural sites and one for urban sites. This is an example of the segment spreadsheet for Center County. The intersection spreadsheet has slightly different columns, however, the general format is the same. Columns A through C identify the site location, such as the engineering district, county, and road name for each segment. Columns D through H provide the state route number, the beginning and ending segment, and offset. These represent the extents of the segment under analysis. Columns I through R represent the variables that need to be collected for the analysis. Functional classification, AADT, and posted speed limits can be obtained from PennDOT's Roadway Management System, or RMS. Other variables, such as the presence of on-street parking and segment type, need to be collected with aerial or ground-based photography, such as PennDOT's video log or Google Earth. Columns S through V show the observed crash frequency for the analysis period. This data was from PSIT or CDART. Columns X, AA, and AB show fatal and injury crashes. Column X shows the predicted crashes per year. Column AA shows the expected crashes per year. And column AB shows the excess crashes per year. These values are determined with SPFs that use the segment input data in columns I through R. Similar columns display these values for total crashes. Column AI shows the excess cost of all crashes at the site. Excess cost represents the economic cost to society based on the number and severity of crashes that exceed what is predicted for the segment type. In the network screening, a fatal or injury crash is assigned a societal cost of $565,107. A property damage only crash is assigned a societal cost of $14,224. These different values result in a greater emphasis on fatal and injury crashes. Excess cost can be negative. A negative value occurs when the observed number of crashes, particularly fatal or injury crashes, is lower than the predicted number of crashes. Locations where excess crash costs are negative are generally not good locations for safety improvements, and funds should be directed elsewhere. For intersection spreadsheets, the final column contains hyperlinks to an intersection's location in Google Maps. These spreadsheets produce the same results as PennDOT's HSM Tool A. There is no need to replicate analysis in Tool A. Rather than using Tool B, you can analyze alternatives by changing inputs in this network screening spreadsheet. Blank versions of these network screening spreadsheets are available from the PennDOT Safety Infrastructure Improvement Program webpage. To obtain a blank copy, scroll down to Highway Safety Screening tool on the right side of the page. Click on either segment or intersection to download a blank copy of the network screening spreadsheet. You can then input the location information, roadway characteristics, and observed crash data to calculate estimated cost for any site in Pennsylvania. The current network screening spreadsheet can be modified to add more sites or to update crash, volume, or geometry information. PennDOT employees can also access the completed version of the county spreadsheets on the internal network drive. For each county, the network screening tool identified sites with the highest excess costs. The network screening team performed safety studies and produced summary reports for the 2 segments and 2 intersections in each county with the highest excess cost. The screening team's report describes the crash history and provides potential mitigation strategies for these intersections and segments. Let's look at examples of summary reports from the 2021 network screening. The 2024 summary reports are similar, although some are 2 pages. This site is the intersection of State Route 2016, or Baltimore Avenue, and Union Avenue in Delaware County. From 2015 to 2019, there were 63 observed crashes. These crashes resulted in an excess crash cost of nearly $2 million. Let's take a closer look. Here we are on the Baltimore Avenue Western Approach looking east. There is Union Avenue. Baltimore Avenue is the major road and has a 3-lane cross-section with left turn lanes in both directions. This approach has 2 signal heads, but only one is prominently mounted overhead. At times, the side-mounted signal may be obscured by other vehicles, trees, or buildings. There are commercial driveways nearby, and buildings on the south side have no setback from the sidewalk. The crash history shows 55 angle crashes. Most of the angle crashes involved a vehicle traveling eastbound on Baltimore Avenue and a vehicle traveling northbound on Union Avenue. Union Avenue also has only one overhead signal. Potential mitigation strategies may include extending the all-red clearance interval or adding a second overhead signal head that is centered over the through lanes. The sight lines on the south side are obstructed, but improving them is unfeasible without removing the buildings. Countermeasures can be simple and low cost, even for a top site with high excess crash cost. This segment of State Route 2006 in Juniata County had a total of 6 crashes, all with injuries. Because the crashes were curve-related, adding chevron signs to enhance visibility may be an appropriate countermeasure. A utility pole on the outside of the curve was sometimes struck, and relocating the pole away from the midpoint of the curve may help reduce injury crashes. These network screening results can help planners and engineers prioritize locations for safety projects with HSIP and Low-Cost Safety Improvement Program, or LSIP, funds. While the network screening lists are not priority lists, the excess crash cost offers useful input for a prioritization matrix. Network screening results can also be incorporated into district traffic engineering studies, including those raised by citizen concerns or those sparked by safety, congestion, operations, or speeding issues. The standardized traffic engineering forms document these studies and often mention crash analysis. Network screening can provide an initial indication of where issues may be present or not present in a broader area. Safety will soon be a part of the Highway Occupancy Permit, or HOP, process. The Institute of Transportation Engineers recently created a new guidance for incorporating safety analysis into Transportation Impact Studies, or TISs. PennDOT plans to follow suit and incorporate safety into TISs. PennDOT's updated HOP guidance will include using Intersection Control Evaluation, or ICE. Network screening results may be used as well. Municipalities may also require a review of network screening as part of the subdivision and land development process. Network screening results can be an important tool when designing projects, when conducting safety assessments, and when analyzing alternatives. Thank you for joining us to learn about network screening. For questions, contact Jason Hershock, Manager of the Safety Engineering and Risk Management Unit.